Welcome to Home Learning. This is Computer Science representing images. This lesson will focus on three different parts. The first part is some information about how images work. There will then be an activity, followed by an exam question which then be reviewed in this lesson. Now over to Mr. Holton, who will tell us more about images.
Images then. So how do we get from a sequence of zeros and ones, which is what computers have to use to store and process data, to an image like this one? And the starting point to understand how are these sort of like little squares that you can probably start making out in the image, these things called pixels. So an image is made up of loads of pixels. It could be thousands, millions, even billions for large pictures these days. And all these pixels have got just one colour. So there's a black pixel that I'm doing now. You can see up here I've got a yellow pixel. There's a white one. I've got a grey pixel. And the number of pixels that I have in an image is important. I've got probably about 20, it's about 20 by 20 grid for pixels here. So the resolution for this is roughly about 20 by 20. But if I increase the resolution, then I can have a higher quality picture like this. So the image is improved, it's a better quality image, but the resolution is increased, which means I need more space now on my disk to store the data for all those extra pixels that I have. And now I'll have trouble sort of drawing squares around pixels because they've gotten so small. So that's resolution. The other thing you need to be aware of is color depth. So if we ever think about a picture here, and we'll just have a nice box, nice straightforward box, and we're going to say this picture is only going to have two colors in it. Two colours is nice and easy for a computer to represent because it can have one colour as a 0 and a different colour as a 1. So let's do that there. And you can see how, okay, that's a 1, that's a 1, so it's going to colour in that way. And this is a 0, this is a 0, so it's going to colour in the pixels that way. Makes sense how a computer can do that. And if I double the colour depth, that gives me access to more colours. So if I draw another grid, but I'm going to double the colour depth and say I've got a colour depth of 4 in this picture. So I've got 4 different options. But I'm still going to keep it the same resolution, so it's going to be 2 by 2. So here's my first colour, that's going to be 0, 0. Second colour is going to be 0. Oops, that's the same colour, isn't it? Second colour is going to be 0, 1. Third colour 1, 0. And the last colour can be 1, 1. Okay, and then the computer does exactly the same sort of thing for each different combination of pixels. It fills in the pixel with a different color, but I have increased the amount of space that I need to store this image now, because if you count up here on this top one here, I've had to use 4 bits here, 4 bits to be able to represent this image because I've got color depth of only 2, whereas here I've doubled it, I've got 8 bits now to represent that. Okay, so resolution and color depth, you increase either of those two things, you get a better quality image, but you also increase the file size of your image. So that's sort of the downside of it. The last thing you need to know about for images is things called metadata. Okay, metadata. That is information included with the image which describes it in some way. So it could be, for example, we send along with an image the resolution. So the computer knows how big this image is going to be. And it could be that we send along the color depth. That is an example of metadata. And there's all sorts of other things that we can send along with it as well, such as what kind of images, what sort of file type it is. That can be included in metadata. But yeah, images have this metadata attached to them to let the computer know exactly how to draw that image when it comes to try to do it. And that's images.
Okay, so now you've heard about images from Mr. Holton, it's time for a task. You should have access to a fill in the blanks document. We're giving you up to 10 minutes to complete that activity. Ready, set, go! Okay, time's up. Let's go through this and have a look at the answers.
Okay, so now you've had a chance to have a go at this fill in the blanks activity, let's see what the answers are. So, images are made up of pixels. Those are the tiny little squares, and each pixel represents a colour. And each of those colours is given a binary code. The code is unique to that colour. Okay, so the way images are made up, it's pixels. Each pixel has a colour and it has a binary code, and that binary code is unique. So for example, a binary code might be 0101, and that may represent red, and 0110 might be green, but there will not be another colour with that binary code. Okay, so let's cross those out. Pixels, binary, colour and unique. Okay, so now let's look at factors that affect an image. The most common ones are colour depth, and resolution. Okay, so to improve the colour quality of the image, the colour depth must be increased. So if you increase the number of bits used to store each colour value, it gives you a wider range of colours, which gives a better quality, but you've increased the colour depth. A higher colour depth means more bits, zeros and ones, are used to store the colour for each pixel. And as I just mentioned, this gives you a wider range of colours that can be used. So if you had a colour depth of 2 bits, that gives you 4 colours: 00, 01, 10 and 11. If you had a colour depth of 1 bit, that means you've got 0 or 1, therefore 2 colours. So the other factor is resolution. Also affects colour size. This is the height and the width of an image measured in pixels. So it might be a resolution of 1024 wide by 768 high. A file, the same colour depth, with a resolution of 1024 by 768, would take blank storage space than a file with a resolution of 1920 by 280. Well, the resolution is lower, therefore less pixels have to be stored, so it would take less storage space. The concentration of pixels is known as the DPI. And that is how many pixels there are in an inch. And this affects the quality of the image as well. The higher the DPI, the better the image quality. An example of this is now when you look at new phone launches, they don't talk about the resolution of the phone because it's on such a small screen. They talk about the DPI, how many dots there are per inch, because if there's a denser concentration, you're going to get a crisper picture and a better image quality. So there are the answers for the fill in the blanks task about images and the factors affecting images.
Okay, next up it's time to complete a past exam question. You've got 5 minutes to do this. Ready, set, go! Okay, time's up. Here's a walkthrough of this exam question. Make sure you self-assess yours at the same time.
Okay, the radio station uses a digital camera to take a photograph of the computer scientist for their website. The photograph is stored as a bitmap file, bitmap image. Describe how bitmap images are represented in binary. So the first thing I'm going to do from this question, I'm just going to pick out the fact that this is a photograph. Okay, so generally we would expect there's probably colors in there. And I'm going to pick out that the photograph is stored as a bitmap image. Describe how bitmap images are represented in binary. So how is it that when we have a picture like this, we can represent a picture which is made up of lots and lots of pixels, little dots, that are each one color each. How is it that, how can we represent that purely in binary? Each one of these little dots gets represented as something. So the key thing to focus on here is that an image is split up, just like this little diagram, it's split up into pixels. So that's the first thing I'm going to write, because that's answering this. Describe how bitmap images are represented in binary. Well, they're represented by getting split up into pixels. Okay. So when it gets split up into pixels, what happens is every single picture, every single pixel gets given a unique binary code. So every pixel is given a binary code. Okay. Now, when I say every pixel is given a binary code, let's say, for example, that I'll make these pixels a bit bigger so you can see them. Let's say we'd zoomed in on an image and it looked a bit more like this. Okay, so we've got 1, 2, 3, 4, 12 pixels here. Let's say that this one here was black, and let's say this one here was red. Let's say this one here was red. Okay, this code and this code are going to be the same because they're both red. Black ones are all going to be the same, so let's say those 3 pixels are black, they're all going to be the same binary code. So what we've got to be really clear with here is each color is given a unique binary code. So each color that is used is given a unique binary code. So let's just have a good look at the question again. Describe how bitmap images are represented in binary. The image is split up into pixels. Every pixel is given a binary code, and each color that is used is given a unique binary code. Right? So every pixel has a binary code, but we're saying that every color has got its own unique code. And this question is worth 3 marks. Obviously, if you know any more about it, it's a good idea to write it down as well, because in a question like this, you don't get kind of penalized if you get a little bit of it not fully accurate. In this kind of question, your examiner is looking to award marks here. Okay, so they're looking to try and get that. Now, we'll just have a look at the mark scheme. Put the mark scheme above it. So image is made up, split up into pixels. Each pixel is given a binary code which represents the color of that pixel. Each color is given a different unique binary code, and metadata is stored alongside the image. Okay, so things that we could have marked here. So we've got split up into pixels, which is there. If we have a look on the mark scheme here, split up into pixels, it's just that one there. Every pixel is given a binary code. Each pixel is given a binary code, and every color is given a different or unique binary code. Each color that is used is given a unique binary code. So you can see, if we have a look at that in a bit more detail, we've got an exemplar model 3-mark answer there. So that'll be all 3 marks.
Okay, that's this lesson on images complete.